A rod can be modeled by the interval from 0 to 6. So in other words, we're thinking of it as one-dimensional. And there's a mass density function given. Density is 1 plus 1/6 x squared. Now the question, what is the x coordinate for the center of mass of the rod? All right, we have some options. 1, 2, 3, 4, or 5. But before I ask for an answer, what can we rule out with confidence, do you think? So you should never, the goal is not to make you just sort of like blindly apply formulas. We want you to think. Let's think about this rod. So we know its density function, 1 plus the 6x squared. So we're going from the interval from 0 up to 6. So let's just pretend like we'll model density by thickness. Where is it dense? Which side? Is it dense towards the 0 side, or is it dense towards the 6 side, or is it about the same? Yeah, x squared gets bigger the larger x gets. So it's getting pretty big on this side. So there's a lot more mass towards the right. So looking at our answers, we should think of our center of mass should sort of move towards there's more mass. That's our intuition. So what does that narrow it down to? Well, where's the center? Just not center of mass, but just literal center.
3.
3. So how will the center of mass relate to 3?
Well, it'll definitely be greater than 3.
It'll be bigger than 3, right? And the problem is asking you where the center of mass is. So which options are we going to say it can't be those?
A, B, probably C.
Yeah, just intuition says these are not reasonable because there's just, the mass is too far to the right. It's pulling us to the right. So now we've narrowed it down to 2. That's good. 50-50. I like those odds. All right, now with that out of the way, does somebody have an answer? D? Did you do the computation or is it intuition? Well, either way, it's the right answer. D. Now, of course, we're coming up on exam season. So one of the things about the multiple choice portion of the exam, you don't have to justify anything. So how you get to your answer, we don't care as long as you get the right answer. So you don't have to carry out computations. You just have to do enough to know you have the right answer. So be smart. Use that to your advantage. Okay, so how do we find center of mass? Well, you need to know mass. That seems reasonable. And you need to know moment. And moment is related to mass, but there's this extra piece about location, where things are. So I like to think of center of mass as being a weighted vote. Hey, where's the mass? So the equation for your moment, it's distance, density, measure. And since it's one-dimensional, measure here is length. Mass is density measure, which is density function times length. So we do our computations. Distance, think of that as location, x. Density function, measure dx. Carry out the computation, do some simplifying, we get 72. Now, obviously 72 can't possibly be right. It's not one of our options, and it's not because you have to remember to divide by m. So run the same computation for m. We don't need the distance, so it's a little bit simpler. Carry out the computation, we get 18. 72 divided by 18 gives 4. All right. Good. Any questions on this one? All right. Well, on then to today's thought for the day. Ashley Brilliant. It's human to make mistakes, and some of us are more human than others. And so, just a fun reminder. It's okay to make mistakes. And it's okay to be a human. We're not trying to turn you into machines. We're not trying to turn you into calculators. It's people that solve problems. And as great as technology is, it's a tool. We want you to be people. We want you to be humans. And so don't get frustrated when you make mistakes. See them as opportunities. Opportunities to say, aha, I made a mistake. I wonder why. And if you look in the history of science and people who create technology, a lot of the greatest leaps forward have come not from methodical working towards solving a problem, but something weird happens and people say, well, that's weird. Or, what? So mistakes are okay, but use them to learn. Our goal is, of course, to make fewer. But that's okay. We'll never get to 0. All right, now, what's our goals for today? Well, we need to finish up our discussion and practice about mass and center of mass. There's still some things left for us to do. And we're going to introduce parameterized curves. We're starting today with what are they. We're going to keep going next time with applications. And so we're going to talk about what they are. And we're going to talk about finding tangent lines and concavity. And there's some formulas here I wrote down. Now you might say, cool, where on the formula sheet are those formulas? And the answer is, they're not there. So the formula sheet doesn't have everything. I know. So it's good to know things, so be ready, because you might be asked questions about things like find tangent lines, find second derivative, when you have parametric curves.
The double derivative?
Yeah, that's what this is. Yeah, we'll talk about it. Yeah. All right. So, we'll jump in the middle of a problem. Find the center of mass of the region bounded by x equals y squared minus y and x equals y if the region has uniform density. Now, this problem is not about graphing, so I'll go ahead and tell you what the graph looks like. X equals y. Well, that's not so surprising. We know what that looks like. What about x equals y squared minus y? What would that look like? Any thoughts? Before I draw the picture? What if I just said x equals y squared? What's that? Parabola. Can you tell me anything about this parabola? Turn sideways, yeah. And so x equals y squared minus y, essentially it's just a parabola. This does a little bit of movement, and it'll go through the origin, so you can check 0, 0 is a solution. It will also go through this point, x equals 0, y equals 1, and it will intersect the curve at a suspiciously nice point. Here, this is at 2, 2. So our region is this region. It's the region between the two curves. All right, so here we go. Here's our region. Now we're told that our region has uniform density. So when it has uniform density, what does that tell us about our density function? It's a constant. Now, someone said 1. Now the question is, what density should we assume? You can put a constant k. Will the constant k change the mass? Yes. Will it change the center of mass? No. And so for simplicity, if you're only after the center of mass, and by the way, we are, I should have pointed out, it tells us to find the center of mass. When we say uniform density, we can just say, aha. We can just say, let's choose a simple density, and the simplest density is 1. Now you might say, but Steve, isn't 0 even better? I thought 0 was a friend. Well, you could put 0, but then you get a 0 over 0 problem. And as we all know, that means more work. So best not to do that. All right, so density equals 1. So if you see uniform density, you can put density equals 1. All right, now, 2 dimensions. Uniform density. Uniform means we can slice either vertically or horizontally. Now, if the density is a function of x, you have to slice vertically because your slices have to be uniform. If the density were a function of y, you have to slice horizontally because the density has to be uniform in your slice. But when your uniform, when your density is uniform, constant, you get a choice. So, should we slice vertically or should we slice horizontally? And why should we slice horizontally? All right. Okay, someone has said we should slice horizontally. Okay, good. Good answer. I like that answer. Why is horizontal a better choice?
Because we just need one integral in this case.
So, one integral. Okay, so think about slicing vertically. So when you slice vertically, you have to go from your top bounding curve to your bottom bounding curve. So if you're slicing up down, well, in this right-hand side, we're going from the parabola down to the line. So that's where we would go. But on the left-hand side, we go parabola to parabola, which means you'd have to split it into two parts. That sounds like more work, which we don't like. On the other hand, when we slice horizontally, we're always going from the parabola to the line. Always the same left side, always the same right side. So it makes more sense to slice in our nice horizontal fashion. So here's one slice. There's another thing that makes us think slicing horizontally, namely the way it wrote the function. So when we see our function written in terms of y, if we see x as a function of y, well, we think we should integrate dy. We say, okay, what does that mean when we integrate dy? That means we're doing horizontal slicing. All right, so we need to do mass, moment, actually two moments, and then we need to find center of mass. Okay, put it all together. Lots of computations to do. Which one do you want to start with? Well, how about, we'll just start simple, right? Mass. Okay, so we look it up and say, well, mass, according to our formula, A to B, and then we have a density and measure. That's what it says on the formula sheet. Now, measure says it depends on what kind of setting you're in, 1D versus 2D. So we're in 2D. So when we think about measure, that really corresponds to area, and that really corresponds to height times width or width times height. So we say, okay, we're going to think of it as width times height. So now we need to start figuring pieces out, assembling our integral. Let's start with our height. So our height is this little tiny piece over here. What will that be? dy. Integrating with respect to y. All right, so the dx or dy should show up somewhere naturally in your expression, so now we found it here. Now let's turn to the bounds. Oh, the bounds, the bounds. Where do we go from? How do we know we go from 0 to 2? Yeah, so we have 0, 0 is the lowest y value, so y equals 0, and y equals 2 is the highest y value. Unfortunately, they're the same for x and y's, but just emphasize it's the y values that we're looking at, not the x values. All right, so far so good. What's our density? 1, because we said density was 1. All right, doing great. That leaves us with just one more thing to figure out. What's our width? So we look at our picture, and I forgot to mark down the formula, so I'll mark it down now. We have x equals y on the right-hand side, x equals y squared minus y on the left-hand side. So the width is going to be this length here. That's our width. So, with that in mind, how wide is that? It should be a function of y because it changes as we move up and down. What would it be? So it would be right minus left, high value minus low value, which becomes 2y minus y squared. All right, so that goes here. Okay, so write it down. 0 to 2, 2y minus y squared dy. All right, so now we have we started with our basic formula. We applied it here. And now our integral is set up. We're ready to do the computation. What's the integral of 2y with respect to y? Y squared. Integral of y squared with respect to y? There's a y cubed involved, that's for sure, but there's also a mysterious gap. 1/3, very good, thank you. And evaluate from 0 to 2. Now, you should always check your lower bound, but it's often 0. 0 is usually a friend, but keep track. You always have to check. When you plug in 0, what do you get? Ah, good. So we plug in the 2. 2 squared is 4. 2 cubed is 8. So 4 minus 8/3. 4 is the same as 12/3. So 12/3 minus 8/3 gives us 4/3. Now, we would pause here and say, if we'd gotten a negative number, would we keep going with our computation or would we check our work? You should check your work. Mass is a measurement of something. You shouldn't get a negative thing out. Moment can be negative, depending on the situation, but mass can't. So good news, it's positive, it seems reasonable, we keep moving on. By the way, when you have uniform density, there's another name we have for mass. What else have we just computed? Area. It's the area of the shape. So when you think of mass, it's like density times area. Since it's uniform density, then it just becomes literally, and density is 1, mass is area. Okay, so next up, a moment. 2 moments. Which one do you want to do first? X or Y? Y. Are you asking why do we want to pick or? No. M sub y. M sub y. Okay, M sub y. You chose the hard one first. My hat's off to you. Good. A lot of people would have chosen the easy one first. All right, now, what's the only thing that changes with moments? Well, the only thing that changes is one new term gets added in. And that is, on the paper, it's called distance. But really, it should be called location. All right, so we have distance, but then everything else is the same. Density, width, height. So when I'm looking for distance, m sub y, what am I looking for? So y stands for what here? This y stands for y-axis. So how far am I from the y-axis? X. So when I'm after the y-axis, my distance is really x. Now, what's my problem here? When I look at what we've done already, we have everything in terms of y. So what we need to do is say, oh, we need to rewrite x in terms of y. Okay, so what x are we going to use? So we look at a picture. We think of this little strip. We say, okay, that little rectangle, that's casting its vote for where the center should be. And what we want is we want to choose the x value that's the center of that. All right, so running out of colors here, but here's the center of our little strip. How do you find the x-coordinate for the center of that strip?
Add two functions and divide by 2.
You add the left and the right, divide by 2. You're averaging the left and right-hand side. So that would be 1/2. Then you add y and y squared minus y. And when we add those together, well, it turns out the y's cancel. We get 1/2 y squared. Okay? All right. So everything else just repeats like it did before. So we can pretty much copy. We just have to add this one piece in. 0 to 2, our x location, 2y minus y squared dy. Well, that's 0 to 2. Distribute through. 1/2 y squared times 2y, y cubed. 1/2 y squared times y squared, y to the 4th. All right, what's the integral of y cubed?
1/4y to the 4th.
1/4 y to the 4th. What's the integral of 1/2 y to the 4th?
1/8 y 5.
It's y to the 5th. That's good. Not 1/8. Someone said, one noted 1/10. Yeah. So add 1 and then divide by the new power. So add 1 to 4 gets you 5, divide by 5. Okay, great, wonderful. Plug stuff in. Plug in 0, we still get 0. Woohoo! 0. Nice. Plug in 2. 2 to the 4th? 16. 16 divided by 4? 4. 2 to the 5th? 32. 32 divided by 10? Yeah, you can write that 16 over 5. And then 4 is 20 over 5 minus 16 over 5 gives you 4 over 5. All right. Well, one more computation to go. What's the last thing for us to do? M sub x. Now, we already have the formula here, so we're just going to cut to the chase. So when we talk about the x, x here refers to what? This x refers to x-axis. What's the distance to the x-axis? Why? Because, if I'm, so this is my xy. To get down to the x-axis, I go y. So the distance becomes not 1/2 y squared, but it becomes y. So it's 0 to 2. Put in y for the distance. Everything else stays the same. All right. Distribute. We get 2y squared minus y cubed. What's the integral of 2y squared? 2/3 y cubed. What's the integral of y cubed? 1/4 y to the 4th. And then we're going to evaluate from 0 to 2. When we plug in 0, we get 0. Plug in 2. 2/3 times 2 cubed. 16 over 3. 1/4 times 2 to the 4th. 4. 16 over 3 subtract 4 gives us, so that's 16/3 minus 12/3 gives us 4/3. All right, now we put it all together. Okay, so x bar, y bar. The bars are the average. So C bars, think average. X bar, y bar is, for x, you use the moment with respect to the y-axis divided by mass. And then for y bar, it's the moment with respect to x-axis divided by mass. It's sort of that sort of backwards thing. All right, so what is our m sub y?
4 over 5.
4 over 5. So we have 4 over 5 divided by 4 over 3, comma. And then, what's our m sub x? 4 over 3 divided by 4 over 3. Now, someone noted, that's convenient. The last entry, 4/3 over 4/3 looks pretty simple. 1. Okay. What about 4/5 over 4/3? What does that become? How does it become 3/5? So if you have fractions over fractions, you can move the fraction downstairs, upstairs, but what do you have to do? You have to flip it over. So it's like 4/5 times 3/4. And then the 4's cancel. That's how you, so you end up with 3/5, comma 1. All right. Now, before we leave this problem, and you're probably like, I'm ready to leave it. Is it reasonable? Well, if we think about it, where would 3/5, comma 1 be, roughly speaking? Well, the 1 says it's roughly halfway up. That seems reasonable. And 3/5, so it says center of mass is somewhere like there. And you can sort of eyeball and say, does it look about right? Yeah, that looks about right. So we're good. Okay. Phew. Well, that only took half a class.
That's way beyond half.
So, well, that's okay. One more thing with mass and center of mass. We talked about one-dimensional, and we talked about intervals, but we don't have to limit ourselves to just intervals. We can think of going with wires. So we can do the situation where we have a wire that has mass. The wire isn't straight, it bends. And so we can say, maybe it's the curve y equals f of x. That's telling us what the wire looks like. And perhaps there's a density function, delta of x, which tells us the density at any point. Now, the good news is we have our formulas. So we have our mass and moment. I just copied them. And we don't have to rederive everything. We just say, well, let's just adapt them. Okay, so there's y equals f of x. So that's the picture. And then you should think of it as there's a density function. So maybe, you know, as you come along, it gets really dense, and then maybe it gets thin again. So there's some density function. So let's set up the integrals to find the mass and the moments for y equals f of x, where this is our scenario, a to b. All right, so let's talk mass first. Well, what should our bounds be? A to b. What should our density be? Do we have a density function? There's our density function. So, go from A to B, density, what's the length? Okay, what's our length? A square root is involved. Very good. Square root of what? 1 plus f prime of x squared dx. Density, length. Add it up. Okay, how about moment? Well, okay, so this is our m. There's two moments. So moment with respect to x, moment with respect to y. Which one do you want to do first? Y. All right, do moment with respect to y. So your intuition says we're chopping this up into little pieces, because that's how integration works. We have this little piece here, and now we're trying to say, where's that location? So we have the location relative to the x-axis, we have location relative to the y-axis. So for y, we still have our integral, a to b. We still have our density and our length. So that part stays the same. The only thing that has to be added is distance, which is location. So what's our location to the y-axis? How far do we have to go? X. So that's our location, and that's our formula that we have to integrate. What about the moment with respect to x? Well, again, we still have the density length as before. So we still have our delta x square root 1 plus f prime of x squared dx. But now where's our location? Okay, f of x, which represents what? Which represents y. So we can just think of it as, well, it's y, and now I rephrase it in terms of the function I'm using, so it's f of x. And we're done. We've set it up. Now, you'll notice we keep coming back to the same formulas, so you can either memorize lots and lots of special cases, or memorize a few basic principles and keep using those principles over and over. I recommend learn some principles. All right, and that brings us to the end of mass and center of mass. I will say they love mass and center of mass problems. So historically, if you don't see it on this exam, you'll see it on the final. So be ready. Be ready. And you're probably thinking, I too love mass and center of mass. But, what about 3 dimensions? Can we do that? And the answer is yes, but not yet. We are saving that for next semester. So don't worry, when you take Calc 3, multivariable calculus, you'll get to do this again. Just when you think you're out, the problems pull you back in. So that brings us to today's topic. We should talk about today's topic at some point. So today we're talking about parameterized curves, and we have to sort of motivate it. We phrase things in certain scenarios like, well, suppose you have y as a function of x. And some curves, and a lot of the curves that we look at, can be described in that way. However, some curves can't be described as y as a function of x. Now, I claim that there is no way to write this as y as a function of x. Why not?
Because we can't normally have more y's than x's you put in.
Definition of function, one y corresponds to one x.
One y corresponds to one x. There's a fancy name for it. Does anybody remember the name? There's a test. Vertical line test, which says, well, anytime I draw a vertical line, I can only ever hit at most once. Now, this is the same idea of saying, if I have one x, I can only have one y. Because the function should be consistent. No matter what you put into the function, it should give you the same output. So if I put in 4 today and I get 8, and I come back in a week and I put 4 in, I should still get 8. I should always get 8 when I put 4 in. So there's a consistency built into functions. So when you have multiple y's with a single x, you can't have a function. Now you might say, well, but do we ever really have to deal with such things? And the answer is yes, a lot. For instance, circles turns out to be very popular. And circles cannot be written as y as a function of x because it fails the vertical line test. So you say, okay, so how are we going to describe such things? So here's what I like to think of it is. Imagine you have a particle traveling through space. So there's a little dot here. And it's just moving through space. And what happens is that the curve is keeping track of where it went. So the curve is tracking the particle. And then you say, okay, what's important to keep track of? Well, we can phrase it as where is the particle at any given time. So we have our expressions x of t, y of t. So where is our x coordinate at time t? Where is our y coordinate at time t? The reason we call these parameterized curves is we're thinking of t, time, as our new parameter. And so we're laying it down. And now we can do all sorts of crazy stuff. So this is a nice generalization. Now, why do I say it's a generalization? Well, we can do everything that we did before. So if I have a function f of x, where I run between a and b, I can write that as a parameterized curve. Namely, I'll have x be t, y will be f of t. And t runs from a to b. So I can do the old stuff, but I can also do new stuff. Now, one thing to note, and we're going to take advantage of this next time, is parameterized curves have orientation. So think of that particle moving. So it's not only that the particle it moves along this track, it moves along that track in a certain direction. So there's often an arrow built in. And calculus is built off of orientation, so that's not bad. So there's this underlying orientation, like the x-axis has an orientation. That's why we put an arrow there. So there's always been orientation lurking in the background. This just means you have to pay a little bit more attention. It's okay that we have that direction. We just have to make sure things work in the way that we think they work. Now, one other thing to keep track of is that there are many ways to parameterize a single curve. Be nice to yourself and choose a simple way to parameterize. So if they give you a curve and say, all right, here's a curve, do some computations on it, you say, what's a nice way to write this curve? Choose the nicest way that you can, because remember, we love ourselves and we want ourselves to be happy. So, all right, some pieces of advice. Any questions about the ideas of parameterized curves? Well, let's try this out. Sketch the following parameterized curve. So we have a few curves here. T squared, comma, t plus 1. And where t runs from negative infinity to positive infinity. Well, let's just start with that one. Now, what can we do? Well, we can do a few things, so there's some suggestions here. So it says, one idea, plot a few points. And then you play connect the dots. In fact, a lot of calculus is built on the idea of like, you can be really smart and plot a few really good points. So a lot of things that we learn in Calc 1 are, if we want to do curve sketching, you say, well, there's some really useful points. If we plot those, then we have a really good idea of what's going on. But even just picking a few points at random, we can get some idea of going on. So you'll see there's a lot of points we could plot. Maybe let's plot a few simple ones. What are some simple values we could plot? Yeah, so when I say plot, pick values for t. T equals 0. 0 is our friend. When you plug it in, what do you get? 0 and 1. So we know that there's a point. 0, 1. What's another nice value for t? 1. Plug it in. 1, 2. All right. 2 points. Aha! We must have a line, right? Well, hold on. Maybe not. What's another thing we can pick? -1. -1 squared is 1. -1 plus 1 is 0. Well, okay, not a line. Now we could pick a few more points, but there's a second piece of advice. Look for relationships between x and y. So here we're thinking of x is t squared and y is t plus 1. Can we rewrite this so that no t is involved, so that no t's were harmed in the writing of the equation?
You mean you could log it, maybe?
So x equals t squared, y equals t plus 1. Well, not quite u sub. So y equals t plus 1. I can solve for t. What is t?
-1.
Y minus 1. So I'm using the second equation because there's just a single t. Now imagine plugging that in. What does that tell us about x? Y minus 1 squared. I would say, oh, okay, this makes more sense. What's the shape? Well, x equals y minus 1 squared looks like what? parabola. So it looks like this parabola, right? So it's just, you take the x equals y squared and shift it. Now, is this the right answer? And why do I even have to ask the question? Is it the right answer? Let's see. There are some bounds here, so you have to sort of pay attention. So we definitely know any points that we plot have to satisfy this relationship. But it doesn't mean that every point that satisfies that relationship is a point that we should plot. Because we sort of hid on some things when we sort of took the t out, we hid details. Now, do we cover all these possible values? Is this, in fact, the whole graph in this case? Yes. Because if you look for y, which y value should we hit? As t goes from negative infinity to infinity, where does t plus 1 go from? Negative infinity to plus infinity, yeah. When you add 1 to any possible number, well, you get, again, any possible number. And so we do cover the whole range. So this is the correct graph. All right. Well, let's try B. T comma t squared. 0 to 1. What does that look like? Well, let's just do the same philosophy. An idea so nice, we can use it twice. X equals t, y equals t squared. What curve do we see? If we put these together, we get, hide the t's away. Y equals x squared. Okay, so that says, oh, I know y equals x squared. It's a parabola. So is that our picture, and why not? It's true that y equals x squared has everything, but do we want everything? We have restrictions on t. Which parts do we want? Well, if we look on, we want t to go from 0 to 1, and we say, well, x is t. So it's not the whole parabola, but it's the part where we don't include 0. We do include 1, so you'll see open circles for don't include, closed circles for include. It's that piece of the parabola. All right. Now, for the last part, xy. E to the t, e to the 2t. Now, if you look at e to the 2t, so we have y is e to the 2t, and I'll go ahead and just do a little bit of fun algebra. E to the 2t is the same as e to the t squared. True story, true story. But what else is e to the t? X. So this is x squared. So we say, aha, y equals x squared. So it must be that. Is that right? No. Say, okay, that's not right. Oh, wait, 0 to negative infinity. So it must be this. Is that right? No. Because that's t goes from 0 to negative infinity, not x. Remember, these are t bounds, not x bounds. So let's look at it. If t goes from negative infinity to 0, what does the x coordinate do? Well, what's happening with e to the t when you plug in negative numbers? It's always positive, but it's doing what? Getting smaller, going to 0. The largest it'll be is at 0, which is 1. So here, this tells us that the e to the t is going to go from 0, but never quite reach it up to 1. So we take our bounds for t and phrase in terms of our bounds for x. So what does that tell us? Well, since x is our e to the t, it is the portion of x squared that doesn't include 0, but does include 1. Now, do you notice anything about these pictures? These two pictures are the same. Which means that B and C, these parameterize the same curve. However, you might notice that one of them looks more pleasant to work with. So this is what we mean by saying, choose nice parameterizations. All right. A few minutes left. So let me pull up an old problem from an exam. Match each of the parameterized curves with the graph of its diagram. So I have a parameterization. I have some pictures here. And the goal is, it's a matching game. Which one goes with which? All right. Now normally we would say, talk to your neighbor, but with only a few minutes left, I'm willing to take any bids. If anyone says, aha, I see that the first one should be this. Or I see the third one should be that. Are there any bids? One should be E is correct. The first one is indeed E. This is y equals x squared. Negative 1 to 1 inclusive. No big surprises. Any other bids? What? 3? You think 3 is D? Ooh, tempting, but no. 3 is not D.
I'm going to go with 4 is C.
4 is C? Nope, 4 is not C. Second is C is correct. We have some arctangent people in the house. Woohoo! Nice. Any other bids? 4 is not A. 5 is not D. 3 is not D. 5 is A. 4 is B. So which one is 3? Not D. It's E.